So today we're going to do some dynamic model tuning with this motor. So it's a direct drive rotary motor, and for the dynamics, well, this rotating cylinder has inertia. And so in order to accelerate the inertia, you have to apply some torque or current. Also, there's a bearing in here. So the bearing has friction, so while you're spinning, there's viscous friction. So it's not an air bearing, so there's definitely friction. And while you're spinning, there's some measure of friction. So today I'm going to use the ACJ. This is ACJ with an arm. So that's the new ACJ Revo 1. And it has an ARM processor, so we can do a PID in it and turn off the velocity loop to do dynamic model tuning. And I have incremental encoder here of a high count per rev, like 540,000 counts per rev. So some very good velocity measurements. This is a nano, of course. The ACJ has a -S for the serial adapter, so USB, SER-USB-S for the ACJ. And so I got the feedback hooked up. I'm running on a 48-volt power supply, and I'm just making some moves back and forth using CME. And so to compensate for the inertia, you have to understand what inertia is. So it's the mass at the end of a radius, the square of the radius. And so I is inertia, or J is inertia for motors or loads, or M is inertia for mathematicians. And so to accelerate this inertia, you have to apply a force orthogonal to it. Blah, 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 Khan Academy. So the shape is very important to determine the inertia of it. So if you had something that was long, it would be unwieldy because it has a high inertia. Okay, so your length gets squared. Oh boy, it feels like a lot of inertia because it has such a long length. But if you turn it on its side and twist it, it becomes a rod, and it's just the radius squared. So this is a solid one, so this is 1/2 the mass, the radius squared. So you got to figure out where the center of mass is and rotate it. Anyhow, that's the one thing we have to compensate for, to apply a current to accelerate the mass. When we're running at the constant velocity, we have to worry about the friction. So the viscous friction is, after you get over the little hump of static friction. Strybeck talks about the lubricants and stuff for the bearings. This bearing is pretty smooth. There's not a big preload on it, so there's not a lot of static friction, so we get past that. And so this small amount of friction is called the Coulomb friction, and then it grows from there. It grows as your speed goes up based on your viscosity. So the friction increases as you go faster. So that's speed related. And of course, another thing in a dynamic model, besides the inertia and the friction or the viscous friction, might be gravity. Okay, so gravity would pull down on something. Mass times the gravity and the radius, the cosine of the angle. When you're flopping straight down, this is rotary, okay? So there's no gravitational effect. If it was turned on the side and you had a mass there that was not circular, then yeah, you'd probably feel the gravitational effects from the center of mass out the length of an arm. So there's different dynamic model compensation for friction, but the basic idea is, if you have something that's disturbing the system, you like cogging, you can compensate for by injecting into the current loop a command. For gravity, if you counter the force of gravity with your own torque or current or force in the upward direction, that would be the cosine of the position, and then add to that some viscous friction based on your velocity. And then, of course, to the summing junction, you want to inject some torque based on your mass or inertia. This is the center of mass over a distance, so don't get confused by M. That's the J or the I for inertia, based on your acceleration. And then you would still tune some loops, but I'm going to show how to bypass the velocity loop, and we'll go right for a PID, computed torque model. So the torque is the inertia, and we got our PID parameters in here, and H is gravity and viscous friction. So let's take a look at CME. We've got this move back and forth, accelerating, running at a velocity, decelerating, stopping. And we can see that I'm using the unfiltered motor velocity because the actual velocity has a filter in it for display purposes, so I don't want to see the lag on that. But you can see how the magenta or the blue is right on top of the magenta, and then it follows. So for acceleration, you get some current. For velocity, you get some current. And when you decel, you get some current in the other direction. And then you hold a steady state position. And so the concept of this dynamic model tuning is to get the following error to be zero all the time based on a perfect dynamic model. Well, of course, there is no such thing as a perfect dynamic model, but this is how we approach it. So you see my VP and VI are zero. So what I've done is I've turned off the velocity loop, but when I do that, I then have to bypass it. So I'm going to use the velocity current feed forward, 32,767 or 32,768 minus 1 is I guess 100% or full parameterization of shorting it out. And then that allows me to turn on some AFF and VFF. These parameters, the acceleration feed forwards, go right to the velocity loop. They go to the summing junction with the PID, but they feed directly into the velocity loop, which is now short-circuited to feed directly into the torque loop. So VFF, velocity feed forward, commands a torque based on your viscous friction, and the acceleration feed forward applies a torque based on your inertia, and you're accelerating it. But in conjunction with just the straightforward dynamic model, we're still going to use PID. So there's some tuning of the proportional and the differential and the integral. And so this box is checked to enable it. I go for the P first, and then I crank up some D. It'll buzz, and then you cut it in half, and then you go for some I, and be careful, watch out for instability. But you can see that while you're moving, because you have acceleration comp, inertia comp turned on, the acceleration feed forward, the following error is minimal. While you're running at velocity due to viscosity, you have the velocity feed forward, the following error is minimal. Same thing with decel, and then steady state gets brought to zero with some integral. Without integral, you get steady state error. So the D term is very helpful for making this look like such a small following error. It looks like less than, I don't know, 100 or 150 counts while we're moving and after we stopped. So pretty awesome tuning. We're going to compare this to doing the PID in the normal way. So I'm just going to turn the PID off and set the. So this is just tuning a nested loop for good performance. I already went through all this, but I'm just going to turn it on again. I don't know, maybe it was 50. So we're going to make this move again. I got to turn off the short circuit on the V loop here. So just set the velocity current feed forward back to 0. Okay. On autonomy, hope it works. Okay, so this would be some tuning based on using your nested loop. Might go for a little bit more proportional gain to be fair. I mean, as your inertia goes up, this PP's got to come down anyways, but you're going from 500 counts. I got it down to 400 counts. The tuning looks pretty good. I mean, the velocity is following. There's a little lag, a little overshoot, but you know, without any integral, you're going to have steady state error. And no, there's no dynamic model compensation in this, and my steady state error is about 50 counts. And I crank up to 500 counts. I could stiffen up my velocity loop. I'm trying really hard to get this normal, just plain old loop tuning with no compensation to approach the 100 counts. But this is looking pretty good. So very stiff loop. It's a little buzzy. Got to be careful of breaking into oscillations. But I cranked it up a bit. I guess that's the advantage of dynamic model. There's some variations and you don't start buzzing all of a sudden, but the proportional is coming down, and let's give it a little bit of integral there. Should bring us into a steady state. So I'm really cranking up the pitch. You can't do this with a large inertia, so if there's a bigger mass than just the motor, that might not be so helpful. But, you know, 200 counts and steady state error, it gets down to 0. Little integral in the VI loop. Integral tends to bounce a bit. So sometimes we turn that off if the inertia is large. And we just get to a steady state that's within a tolerance. And this one looks like it's also down to 0. So there you go, kind of a comparison and contrast between nested loops or just plain old PID and no feed forward terms injecting into the current loop for dynamic model compensation. Okay, thanks for watching.